had it paused. So the first thing I want to do this morning is get into a demo and look at the I/O path. I want to talk direct I/O first. And when you're doing striping and doing XVM, you're primarily looking at direct I/O. In fact, as I mentioned yesterday, this Oracle times 10 site, the times 10 was doing checkpoints of the time 10 memory stuff, and they were checkpointing more often than the file system could handle. And I do have a system info gather from the site if anybody ever wanted to look at one. And that's something I wanted, I didn't get any time this week, but Mike and Carlos, I've added a whole bunch of stuff to System Info Gather and can give you a real site example, and you can poke through and see all the command outputs and ask questions on any particular type of command output that I've added into the System Info Gather. Don't be afraid to continue on with the content and the subject of this class after Friday. Don't be afraid to come back to me. I'm trying to apply what I'm trying to do. So just starting off on the left, we start off in user space, and I've got two places where the data can exist. The first place is where the data actually resides, whether we're talking an array or a variable. And it's either a static initialized data that's in the data segment, or if it's dynamically allocated with malloc or mmap, and those are in the heap. So static is in the data segment, dynamic is in the heap. But the program could also have data in the stack. Now the stack is what we use for subroutine jump and returns. Every time I jump to a subroutine, I save the prior subroutine's environment variables and the local environment, that subroutine, onto the stack. I push it onto the stack. And then when I exit from that routine that I jumped to, I use the stack and pop off the stack the prior subroutine's environment, reinitialize it, reload those local variables, and then return back to the prior routine. But we also have automatic arrays that can be on the stack. We look at the stack with debuggers like TotalView, GDB, DDD, that sort of thing. And the process could also have data that's in shemem or dev shemem. So that's where the data is starting with. In a Fortran environment, again, we've got a library buffer. So the FFIO has the ability, there's a little arrow here. FFIO has the ability to trace this path and see the Fortran to glibc calls and characterize what the Fortran reads and writes look like as they're being presented to glibc. So there is a profiling capability in FFIO. And FFIO originally came from Cray, and one of the key things it was meant to do was to be able to control my I/O attributes without recompiling my application. I mean, FFIO goes back to the 80s and stuff, and we would have benchmarks where the rule is you can't change the source code, but we wanted a way to be able to manipulate the I/O characteristics, the I/O attributes, without recompiling the application. So they added an I/O layer called FFIO, and you kind of preload the FFIO library, and then it intercepts things, and it allows you to control the size of this buffer, for example, whether we want direct I/O or cached I/O. There's a profiling layer, and we can even turn this buffer into a cache, what they call EIEIO. It's kind of a joke. Old MacDonald had a farm, EIEIO. And EIE management of this buffer actually turns it into a cache. And then this is a private in-memory cache. Nobody else can step on that cache because it's private to you. At any point, at some point, we've got either a print statement or the library buffer is full, and then we make a system call. When we make a system call, I've got kind of the system calls. Get DNs is getting your directory entries. Then we have an open statement. And the open statement is going to create an open file table entry with the file descriptor being the offset into that open file table. We got something to get status on the file. And then we got our normal read the file, write the file, and then when we're done, close the file. Now, one thing different between IRIX and Linux, by the way, in IRIX, when you close the file, it's released from the buffer cache. In Linux, when you close the file, it stays in the cache, thinking that somebody else might use it. And we need to look at that aspect today when we get into buffer cache. Also mentioned random IO, append, rewind, truncate, and that would be the sync command. There's also IOCTL, and in particular XFS CTL system calls. One of the things that the XFS CTL system call can do is ask the operating system what a friendly IO request size is, so that I can figure out, every site's going to have a different design file system. My application can ping the OS and say, what do you consider friendly IO? What's your stripe unit? What's your stripe width? What's your blocking characteristics? And that's what we're getting into right now. Now, there is a special XFS development RPM that has to be loaded in order to use that interface. What's called get DIO info. We also have direct IO then, so pread and pewrite is where we're going right now to deal with direct IO, and then later today with the buffer cache, we'll look at standard reads and writes. And then we also have asynchronous IO. So strace is going to tell me about these system calls and profile them. Again, remember, strace has a lot of data being written. It will throttle back your application. So any sort of interactive performance problem you're having, because the program that you're going to look at is dominating the system, it has high I/O intensity and is able to basically maroon the interactive user, creating a degradation in interactive response because the interactive user can't get buffer cache because the buffer cache system calls or library calls are busy, high contention within the buffer cache. So strace, you may have a problem you attach with strace, that program then gets throttled back because of the strace data being written, and whatever event that you're trying to look at has subjectively gotten better because of the I/O intensity being dropped from the process that you've attached to. Does that make sense? Are we okay with that? Now, the other thing that is going on here is when we transfer data from user space to kernel space, we actually have a memcopy routine that is going to copy the data from the array space into the page cache. And that memcopy, or it used to be called like bcopy and stuff, is a disadvantage on UV because that memcopy is going to probably go across the interconnect. And again, every time we go across the interconnect, we have a degradation in our latency and our performance. Now, this drawing isn't quite right. This direct should probably go down into the system calls. But what I was trying to say is direct I/O does not do a memcopy. With direct I/O, we're going straight from the array, straight off to the device. Whereas the default buffer cached I/O is going to have a memcopy, and then it's going to copy it to the page cache. So this is my drawing, but it's not. I'm not always happy with it. Again, once I make my system call to initiate the I/O, I've got three types of I/O again. I've got my default, which is through the page cache and memcopy. I've got direct, which is going to go straight from the array off to the volume manager and bypass the buffer cache. But I also have raw I/O that's going to bypass the file system, but it's still in the page cache. So three types of I/O, three different paths. Okay? So at the fourth level here, we're really talking about the file system interface. And here again, the virtual file system is going to figure out whether we're XFS, Extended 3, NFS, BTRFS, and then call the appropriate kernel routines for that type of file system that understand that file system structures. So we're really talking in this layer the metadata. And that's where I need to go next. I'm going to do direct I/O, then metadata, then cached I/O. So in the file system, we're interested in inodes, directories, we're interested in the journal, and we also have the slab issue. So the default path is from the array to the page cache. And again, page cache I used to call file system buffer cache. To me, file system is the metadata. Buffer is the right path to do the sectorizing. The purpose of a buffer is to hold the data and make it well formed or block it. And once it's blocked, send it on to the next stage. In a write path, we would normally call this thing like a lazy write or a delayed write. When I'm doing cached I/O, I don't have to worry about it being blocked or on a 512 byte boundary or a 4K byte boundary or anything like that. So we need to talk about file system allocation units and stuff for the blocking. So by doing the cached buffered I/O, the buffering is basically blocking or chunking up the data into well-formed friendly requests. And again, 4K, 64K are the two common ones, but 4K is real small. Again, if I'm moving a large amount of data, I say I don't want to move a terabyte of data one block at a time. I want to up the request size. I don't want to spend all my time in handshake protocol to move the data. I want to do it in big chunks, but I don't want to do it in too big. This is where I was talking about, like, comparing it to feeding a baby. If I give it too big of a spoonful, it's going to choke. If I don't give it enough, it's going to starve. So this is where we get into understanding well-formed, sectorized, blocked type of I/O. So once it's in page cache, we then have, if it's write, we have the flush daemon that's actually doing the delayed write and flushing it off to disk. And this is what we have to get into, and that's the lab that I want you to work on today, is the flush daemon. So at this fifth level, we had SAR-B, SAR-R, and XFS stats. And I need to get into XFS stats today. But SAR-B would tell me about reclaims and stuff. And SAR-R tells me how big the cache is in the slab. But again, SAR-R doesn't break my meminfo out in detail, so I like it to be actually just proc meminfo or the PM chart that I showed you, or that memstats command that I wrote. So this is what we're going to get into. We're going to do direct I/O first, then metadata, and then the flushing and the cache behavior itself. And I spent a lot of time earlier in the week on proc meminfo, but now today I want to get into the dirty, the write back, the NFS unstable, and the cache clean. And remember how many different things were in the cache field, including in top, the slab and stuff. Any questions right now? Now again, direct I/O does not go through the cache, so these variables do not affect direct I/O. You will not see anything dirty, write back, or clean in direct I/O. It's going straight from user space, straight off to the device. So I'm going to come back to these later, but the biggest one that people have to worry about, dirty ratio and dirty background ratio. All large memory machines, I would drop these down automatically to begin with. I don't want half my memory to be dirty. So dirty ratio is the maximum amount of memory that can be dirty. And again, dirty memory cannot be recovered until it flushes with the sync command or background ratio. When you hit dirty ratio, your process gets put to sleep. At dirty ratio, the operating system is saying, I'm putting you to sleep. You're choking me. I don't want any more dirty data from you. I can't handle it. And again, on a 16 terabyte machine, the maximum hard code that dirty ratio can be is 50%, but by default it's like 40%. So in a 16 terabyte machine, we're talking about, 6, 7 terabytes of dirty data. And you're going to choke on that. When I'm talking about flushing, there's two ends of the spectrum for me, a trickle flush or a flush choke. And I want to be ahead of this data and trickle flush it. I don't want to have it get backed up on me and then storm me and choke me with all the flushes. And again, there is a theme of
But
this.
if your application mix is such that there's no interaction between those datas, then effectively the more data in memory, the better for the applications. And as long as there's no overlap, then even if it does go flushing, it shouldn't really bring the system to a halt, which it does seem to these days. But I don't see why it should, even though it's flushing huge amounts of data.
Yeah. Well, there are several things going on here, and I can't get into the details without actually looking at a particular situation. But again, that memory is unavailable. And if I'm in a CPU set and all my memory is dirty in the CPU set, I can't get memory. The trims are not going to work on me. There's nothing to trim.
But as long as I'm not showing memory pressure, then there doesn't seem to be anything wrong with having a huge slab or cache, whatever.
True, but every time it's on a per node basis, and every time I get into a node trim, I'm going to hit the slab first and then the dirty. Now, the other end of the spectrum, in your case, if I'm doing read-write, read-write, or read-write-write, then slowing down the flushing so that I can solve everything out of page cache makes sense. But in general, you don't want to get it overrun. And again, we have to look at that trim wait time with things like get delays and watch for K-swap-D, but remember it's happening on a per node basis. So without getting into the details of a particular situation, that's the best I can answer your question right now. And let's see what happens when we try to do it. But anything that tries to do a sync or a flush and anything that needs memory isn't going to be able to do anything on that dirty. And I had this one side USPS that would do a sync on the serial console connection, and they had 4 terabyte of dirty data, and then the sync would lock up their system console for 45 minutes. And part of that was also the large slab. And trimming the slab is not very efficient. We saw it took like 15, 20 minutes to trim, what was it, an 80 gig slab earlier in the week? So I'm not disagreeing with you, I'm just trying to twist it into my perspective. Well, let's see what we can generate today for a problem. But again, I just don't want my dirty data to get too far ahead of me. So dirty ratio by default is 40%. I cannot have more than 40% of my memory dirty. The highest it can go is 50%. And the lowest it can go, it's not shown here, but we now have an underscore bytes, so that on large memory machines, instead of percentage, we can do it by an actual byte size and get a better control of that dirty ratio. So I'm going to come back to this later, but dirty background ratio is the point at which we start flushing. So if dirty background ratio was at 50%, we would get 50% of my memory dirty before I even start flushing. And if I'm in a CPU set that is smaller than 50% of my memory, that entire CPU set is going to fill up with dirty. And then I'm kind of deadlocked because I don't have room in my own CPU set to get memory because it's all dirty until it flushes. So background ratio is the point at which we start flushing. Dirty ratio is the point at which we put the process to sleep and say, don't write any more data to me, you're choking me. We also have min-free kbytes that says start trimming when we hit that min-free kbytes. And again, Mike, you were seeing it was much larger than what min-free kbytes look like. I do have a PV on this because in my past testing, it was not accurate. It was actually double the size of what I expected. And I haven't tried it on this kernel yet. So min-free kbytes is the amount of breathing room that I leave for the OS, including the TCP stack. And it's not on a per node basis necessarily. Then we've got dirty expire centiseconds. This is 30 seconds by default. So any data that has been written into the page cache and has had a mem copy and copying it into the page cache will stay in the page cache and will not flush until it hits either dirty background ratio, dirty expire centiseconds, or a sync or flush. So again, I can slow down my flushing if I'm in a read-write-write or read-write-read-write and I'm getting a lot of write cancels. I can slow down that flushing with the dirty expire centiseconds, but then that also increases the risk of corrupt file if I take a service interruption. Ooh. Min slab ratio is the maximum that the slab can grow to. Again, the smallest you can get to right now is 5%, and 5% of a large memory machine is a lot of slab. And we saw when I hit the slab earlier this week, it took 15 minutes just for a 100 gig slab. Imagine a terabyte slab or something like that. And it's well known that the slab trim is not very efficient. And when I do a trim, the first thing we're doing was hitting the slab. So I may end up, I wanted to grow the slabs overnight, but I may end up doing that tomorrow to see what we can do. Get the slab real big again and then get into the memory trim situation. We also had VFS cache pressure, which was controlling the balance between the cache and the slab. When I get into a memory trim situation, I'm going to go to the slab first and then the cache, and then the processes. So this kind of controls the balance between how aggressively do I trim the slab versus the cache. And then again, swappiness was between the cache and the processes. So VFS was between the cache and the slab, swappiness was between the cache and the processes. And there's also one called zone reclaim mode. And this has given problems in the past on Lustre servers and stuff like that. But let me come back to that. Any thoughts or questions at this point?
Yeah, the minimum 3 kbytes.
Yeah.
Essentially, if I'm overrunning and filling up the memory with dirty data, essentially, and I'm way above my dirty ratio and things are going on, but I'm still managing to fill it up, that's to salvage that situation, is it?
No, dirty won't go more than 50. But it is resolving things like if all my memory leaked from a shemem, for example, or again from anon pages being grown. So I'm just saying dirty can only be 50% maximum. The other 50% could be occupied by shemem or anon pages. So at some point we start trimming based upon min-free kbytes, and then after the trims are unsuccessful, we've trimmed it as much as we can, then we start swapping. Does that answer your question?
It's not clear to me, I have to say.
There was a lab for it, but again, in the lab, we were doing it all with the non-pages with memhog or that code 4 to be able to allocate all my memory.
Right.
But this is the trigger point at which kswapd kicks in and tries to do something. So when min-free kbytes happens, we're going to try to keep a certain amount of memory free for the OS, which means a trim first. So we're going to try to trim buffmem, try to trim the slab, try to trim the cache, and then we start swapping the processes. So this is a trigger point for kswapd, whereas dirty ratio and background ratio is a trigger point for flush. So dirty expire centiseconds is also a trigger point for flush.
So seeing kswapd is real trouble because that min-free kbytes is down at 134 meg on 70 and 80 gig machines.
Not exactly, because kswapd is running on a per node basis, and min-free kbytes is not on a per node basis. So there are triggers for kswapd to come in on a per socket basis and manage the memory on that socket.
In addition to min-free kbytes?
Correct.
So the backstop is min-free kbytes, but I've had earlier triggers on individual nodes? Correct,
yes.
Yes, okay, yes.
So there's a kswapd on every node, and it's going to manage that node. So we were running out of memory in our login CPU set and could see kswapd being busy in there for that. But we weren't at a min-free kbytes yet. But the other day when we saw this, the mem-free on that particular node was still much larger than min-free kbytes. So a lot of these dirty ratio, dirty background ratio, a lot of these thresholds are not on a per node nor on a per CPU set. They're just system-wide. Any other comments? Well, let me move on. So once we're in the page cache, then we go to the volume manager. Or if we're doing direct or raw, they also are going into the volume manager. And this is what's converting our logical to the physical.
Just one question, sorry,
yeah.
just going back.
Yeah.
I know we keep opening RFEs and that for sensible tuning suggestions at these things. Are we actually getting anywhere? I mean, now, given the number of sites you've been to and the number of machines you've seen and the size of memories that you've seen against disk farms you've seen, are you now able to give a sensible set of those values for different configurations and say this is about a 75–80% good ballpark set?
Rough rule of thumb, yes, but they're really not. I myself have several RFEs in this area, but it's such low priority it's not being addressed. But the other issue here is that every site is different, and again, knowing my workload characteristics helps me make better decisions than a default.
Yeah.
So they are intending to drop these things down. I've seen dirty background ratio go down to 5%. But again, dirty ratio and dirty background ratio can go by bytes now, and those are not being used by default. And again, you'd have to know what the bandwidth of your file system is to be able to make a good decision about how to set these.
Yeah.
I generally want to know how big am I willing to get it such that it can flush to a given file system in a given time frame. So if I'm doing a checkpoint and I know how big the checkpoint is, and I know how fast the file system is, I might be able to get a reasonable setting between the two, but it's not something that can be done automatically.
No, indeed, because just effectively changing one has got so many implications that every time these things come through and I have to do dump analysis for the stuff, which is constantly, you're loath to suggest any tuning changes because they're so interconnected that you can put the site out of action almost without some kind of previous testing time. Yes,
I agree. And these problems get more severe as the systems get larger and larger, more CPUs and more memory.
Yeah.
The impact and the swing of the system gets more extreme. The intensity gets much higher. And the effects get more noticeable and severe as the system gets bigger and bigger. And I do defer a lot of this to Hattie in terms of trying to get some sensible ones. The biggest one that bothers me is slab ratio right now, because I don't like to see these slabs in the terabytes. Can we move on?
Yeah,
Go ahead and ask a question if you do. But so anyway, at the volume manager level, I only get XVM statistics. And those are really no good anymore. I want to demonstrate that today. The reason they're no good anymore is because we're going through the elevator and the blocking layer twice. First the XVM blocking layer, then the device blocking layer. And XVM is blocking it before it actually sees the statistics. So I've got an RFE in this area saying that those stripe alignment statistics aren't any good anymore. And that's what I need to show you in the demo coming up. From there, then, we get to the elevator. This is where the proc disk stats statistics come from. SAR-DP, top disk, IOStat. A lot of people still use IOStat, but the thing is SAR, I've got historical data too. IOStat doesn't. IOStat was written before there was even a SAR command on Linux. So it's kind of a legacy leftover. But unfortunately, SAR-D does not show merges, and IOStat does. And that's the only real advantage to IOStat. By the way, I should warn you, listen to this carefully. The first record, the first report of IOStat is since boot. So if I do an IOStat 1/5, the first sample will be the delta from the time the system booted, and then the rest of the 3 samples would be the delta in those 1-second samples. So some people get burned by that. The very first sample of IOStat is a delta from boot to that first sample. And then the rest of, IOStat 1/5, so you get 5 samples. The first one would be from boot, and then you get 4 deltas during those 1-second intervals. So I'm trying to get to that as soon as we can here. The next layer then is the device driver itself. So we can see each individual IOP with block trace. And again, that hasn't been working in the past. I may poke at it today. For time reasons and stuff like that, I'm not sure how much time we're going to get into that. But this is going to basically give me statistics on each individual IOP. So in the proc disk stats from SAR and top disk, you're getting an average, and I might get 1,000 little writes and 1 big write, and the average doesn't correlate between the two. At the block trace level, I'm able to see each individual IOP operation, including where it is and how big it is, where it's positioning to. Again, there's SeqWatcher that can plot that sort of data. And again, at the elevator or device driver level, we've got that device attr.conf file that can control, in particular, max sector kbyte is the largest DMA that I can do. So that device driver is limited by max sector kbyte. And the problem with XVM statistics is that the first layer has max sector kbyte drop down to stripe unit size, and we're blocking it on the first pass through the block layer. And then XVM doesn't see what was presented at that first layer. Max hardware sector kbyte is the largest that I can increase max sector kbytes to. So that's my hard limit. And the older XVMs, the default and the hard were the same, so I was not able to up them at the XVM layer. But that got fixed so that I can now up max sector kbyte to get my DMA bigger. And again, I don't disagree with engineering saying let the first layer do the blocking. I'm just trying to explain why the statistics are not relevant if you were used to them from the older days. QDEP, command tag queuing, how many IO operations, how many IOPS am I going to queue up on the controller or the spindle. Read ahead kbyte, if I'm doing lots of little random IO, I might not want read ahead kbyte. And then the type of scheduler. We didn't get a chance to look at this yesterday, but take a look on your Floyds and look at ITSI, devattr, devattr.conf. And you'll see certain types of devices that are a no-op as a scheduler. And then from there, we can get into, if it's the base disk, SG mode tool is looking at that cache and the PROM that's on the spindle. Again, we have a write cache bypass capability, which is going to slow down my application because I'm going to get the I/O done when it gets to the media, rather than the I/O done getting from the cache. And the disadvantage to that is the write cache off will slow down my I/O. But the advantage is that I am reliable and know for sure that my data made it to the media, made it to the spindle. And then if it's a RAID, looking at SME GUI type of stuff. By the way, I ended up doing a reboot on Floyd 3 yesterday. I panicked Floyd 3 yesterday using a XVM command. There is a PV on it. But once I rebooted, SME GUI worked. So I'm suspecting that we had an event or something like that that impacted the SME agent and the SME monitor that was running on Floyd 3, and that's why it got unresponsive yesterday. I also do see Java errors when I'm starting the SME stuff, so I'm a little concerned about that. But again, I'm putting SME software on /11 SP2, and I don't know that it's even supported for that release yet. Anyway, do we have any questions about this slide right now? So I'd like to go off and actually do a demo here, and then we're going to take a break, then we'll talk XFS, take a break, and then talk buffer cache. That's the agenda for today. Any questions? So let's just see what I got here. I still have my PM chart running from yesterday. Oh, this is Floyd 2. I want to really go to Floyd 3. I'm just looking here. Let me close them all, start again. And again, I already have pre-built scenes. I didn't do it in this class, but those scenes that I built are ASCII text files that can be shared. You can see where some of them, these are the defaults. I'm going to click here. And in Windows here, it's in my document settings, DAW.pcp PM chart. And these are ASCII files you can share with somebody. So let me just check on this one. Oh, again, I didn't select the proper host. And let me create another tab. I do like the tab capability. You can only get so much on one screen on the desktop, but by having tabs, you can flip between things. Again, I already am using ones from the earlier in the week. For this one, I'm going to do a new chart and go to the UV group, go to the NumaLink traffic. By the way, we didn't really talk about this, but under UV, you can only look at one thing at a time, and the default is NumaLink. There's a hubstat command that would allow you to switch it to look at cache coherency, directory memory, stuff like that. So I'm just going with the default and the linkstat-uv command, and I'm just going to go with the send bytes this time. 4 ports per hub. And again, the other problem here was it didn't show where the port went to. There was an old tool in IRIX days called OView that would actually show the point-to-point connections, but the systems got so big it was hard to render a view of that. And this one I don't really like to do a stack on. I kind of like to see them just plotted like this. Let me just show you. I'm going to edit chart and go to a stack. Particularly on a large memory machine, there'd be so many ports. It's really impossible. Here, let's just see here. So I can see that one is this port. That one is that port. But I myself just don't like to view it that way. And here I'm only looking at 4 blades, not, 128, 256, 512 blade counts. Too many ports to look at. Let me just leave that alone. Let's also add a tab. This one I'm going to call VMstat. And by the way, I'm a little surprised the NumaLink traffic came up. Remember, by default, it's off, and you have to use the linkstat-uv-A to actually turn it on. This one I want to go to memory, VMstat, and I'm just going to throw a bunch of them on here. Kswap-D. And, Mike, the other thing is some people don't like to do this with the class because these behaviors we're talking about are constantly changing as we, get newer kernels and newer rev levels. And that's kind of why I like to run the class on the new system to see how it behaves. So I'm looking for trim statistics here. Here's my page scans. That's my trim, Kswap-D activity. Page steals, when I actually do a swap or a trim. And that looks good. This is transparent huge pages. Oh, did I get slab scanned? Okay. Now, one of the things that's bad about this is that one of these numbers might be in the 100,000 range, but another one that is real critical might be in the 10 range. And I am a little concerned because I want to make sure these statistics are working. So I have a ASCII script called vmstats that will show me the data in a delta. And that way I can compare what's going on with the vmstat file versus what PCP is giving me. Let me save that view, by the way. Let's see. I wish there were the ability to actually save a config file that has all the tabs configured at once, so I could just say open this view and it would open up all the tabs and everything. So this one, let's see, I think I had Alex stalled already here. Yeah. Again, the NR number of pages, I still am using meminfo rather than these, but these are in 4K byte page sizes. There's some interesting things in here. Some of these are new, but I'm not going to look at them right now. But I'm seeing a lot more in there than meminfo gives me. Okay, page activates, page deactivates. This is, again, the swappiness. I don't have a written lab, but I've done demos where I change swappiness and watch the balance between active and deactivate, and then the actual meminfo that has the amount of memory that was in an active-inactive state for page cache or file cache and non-pages. Let's do a page fault, page free. Pages paged in and pages paged out is really I/O. That's not swapping. That's total I/O. That's really the what PCP is already giving. That page in and page out is really what we're getting here. Total IOPS across all disks. Let's see, anything else I'm interested in? Oh, I wanted major page faults in here. Major page faults being to disk. Page fault is a TLB miss. Page rotate I'll stick in here. Activate and deactivate should have a correlation to page rotates. And then here's the actual swapping. Pages swapped in, pages swapped out. And that was SAR-W, SAR-big W. I'm just curious if a zone reclaim failed is relevant too. I don't find PCP very friendly to do the node info type of stuff. Okay, I'm just looking at the numbers here. Pages freed, page faults. You can almost see a correlation between the page faults and then something being trimmed or free. Oh, look, we had a trickle swap in that just happened. So there's stuff out on swap that's trickling in. If I look at memory, I still got lots of memory available. Okay, let me go back here. Let me save this one. Let's see, I don't think I really need anything more right now. But this one still bothers me, that some of these VM stats may not be working right, but that's what we're going to find out here. Notice I do have some stuff out on swap too. So now let me get to the system here. Oh, one other thing I usually like to do here, chart, no. Edit samples. To me, if you look here, these are pretty wide bars to me. And this is all personal preference, but I like to see more data. I don't want them, this is about right. Now if I actually pulled this out and did it this way, then I might even go a tighter sampling interval. But I want to be able to see as much data as possible. If, however, I get a storm like this one, well, this isn't really a storm, but there could be stuff, see there's a little stuff buried down in there. I can get rid of this and look at it. But there are times I may shorten my sample interval to push a storm like that off the chart so that I can drill down into this and see it better. Okay. I'm not going to record that because I don't want to take up disk space on my Windows system right now. So, I want to do an analysis here and see what's going on with the system. And then I want to do a direct I/O experiment. Taking a little bit to log in. I do see a little bit of system time. I do have lots of memory. Looks like the slab is the biggest thing. Let's go to memory here. Get rid of free. I already have a 35 gig slab. Let me get rid of a non-pages. About a 34 gig slab. Am I able to get, there's the login prompt. Again, remember I'm running in a boot CPU set scenario. So Mike, you mentioned you didn't feel any impact. Well, we do have an impact right now. So let's just start off at the beginning. I like PM chart running in the background because that gives me historical. So I'm really not interested in user time, but I do see system time about 5%. I do see some I/O wait time.
Yeah, you've got a load of them test programs running on there. Code 2, MP static, Code 5's running.
Yep, that's fine. We'll get there. I'm trying to get a more complex scenario going on, and again, characterizing what's going on.
Yeah.
Even here now, I am feeling an interactive performance occurrence. And look at, I'm just sitting here. There we are. If I did have crash on the other window, I should probably bring up another window. I could look at this to see what it's doing. The hard part is to be able to catch it before it goes away. Okay, so looking at this, and again, be aware that I'm in a CPU set situation, but I'm only using 15% of my memory, a little bit of raw I/O, and again, I've got a 28 gig cache. Okay, now I'm just going to go on *big S 1-5. While I do that, let's SSH to. And I did something to Floyd 1 as well. So here again, I am feeling an interactive performance event, just a little. So I got about 9% of my swap free. Notice that I do have stuff that's both out on swap and in memory. And what do I got here? About 4 gig that's out on swap on a 10 gig swap. I'm going to do a *big W 1-5. Again, I can feel the interactive response issues. Not seeing, oh, there's a swap in. There's a swap in. This is what I refer to as trickle swap. By the way, I am feeling interactive performance events. What do you think I should do? let me do it this way. Cat / proc / $$CPU set. Even that's taking time. I'm in a login CPU set. So to help myself along, and again, my MindGetty in this case, or SSHD, is still in the boot CPU set or the login CPU set, and they're still sharing the same memories node's memory. So I'm going to echo $$ into /dev /CPU set /tasks. And that'll protect what I currently have, but that does not protect SSHD, the master one, or MindGetty. They're still in the prior CPU sets, not globally. I could see putting MindGetty into a global just by default. So you got a boot CPU set, a login CPU set, but if I connect in through the system console, that login automatically goes to a system-wide CPU set to protect it from a particular node that might be out of memory. Okay, so now let's just try a SAR 1-5. You can see it's snappier now, subjectively. Okay, SAR-R 1-5. I'm just going through it quickly again. 15% of my memory. Again, one of the problems here is that SAR-R doesn't give me what I want. It's not detailed enough. It's still a 2-4 kernel mindset. Let's do a SAR-B 1-5 just to look at this. This is basically the disk stat data summarized. This is basically what you had in PM chart. I go back here. The SAR-B is basically this IOPS over all disks. And I can see it bursting. You can even see a correlation here. By the way, I can see where we dropped some data for a while too. I'm going to do something here, ps-e, grep for PMCD. I'm going to echo 5376. And I'm also going to echo -17 into but there are a lot of times you can't log in interactive, but the PMCD daemon, if it's up and has memory, you can still connect to it. So I'm hoping that will get it out of the boot CPU set and reduce some of this pressure here. Now, as I'm talking, that's taking time, and workload conditions can change, so I will often go back and see if I'm still in the same scenario, same behavior that I was looking at when I started. So anyways, I looked at CPU, I looked at memory, I looked at swap. By the way, I was going to do a SAR-big W, and you can see trickle swap again that's been going on all night. This is what I refer to as a trickle swap. And even though I've got plenty of memory available, in here, when I just started here, I can start to see swap activity more, even though SAR-R shows that I'm in a low memory utilization situation. I can see a memory trim, it looks like, that happened right here as well from that. So again, this SAR is not helping me on a per CPU set or node basis. Okay, I want to just move on here, SAR-DP 1-5. Let me do it without the P first, 1-5. And I think I'll just leave the fonts the same right now and live with the line wrap. And what I generally do with a large disk farm is just go to the averages. So when I don't have the P, that's my major minor number. Now how can I map that major minor number back? What can I do to map it back? Proc partitions is the easiest way. So what did I have there? 896. 896 is SDG. But now I need to figure out what SDG is. I'm going to come back to that later. This is where figuring out your file system layout makes sense.
We learn 11.
But let me get back to the file system layout design after I finish this triage. So this is major minor numbers, but if I do a SAR-DP, and again, if the minor number is real big, I think it was like if it's greater than 256 or something, you may get a case, and there's a fix for it from HEDI, where some of these show by name and some of them show by major minor number. So looking at this again, not too bad. Again, I like these to be less than 60, and I like this one to be less than 100. I'm seeing 13 and 16 here. Well, here's one that's at 92%, 15%. Okay, 13%. What is SDC? That's at 92%.
That's LUN 12.
It won't help me here. SDK is there. So now the hard part is going to be, let's do an HW info --disk. Let's grep for device files. And I'm looking for SDC. So I'm trying to figure out what file system is. I already know it's in Scratch, but let's get there. Again, if I can catch this, let's bring up a top in this other window. Again, I'm experiencing an event here. Look, I'm kind of locked out. I'm not getting any response. So there we are. Let me get out of that CPU set. See if I can bring up top now. It came up quickly that time. So I am seeing, look at the load level on the system right now, but that is not my performance event occurring right now. 6 processes running, low user utilization, low system time, but again, I'm within a CPU set. A little bit of I/O wait, lots of memory free, but notice I need to know that I'm on a CPU set and the average size of my blades, or my nodes, I'm sorry, is like 36 gig. I have a 28 gig cache right now, which again does include the slab. We're not there yet. And I am seeing code 2 MPs running. Notice the percent CPU is larger than 100%, indicating it's multi-threaded. And they've been running for a while. I'm going to do a capital H. Capital H is going to show it by threads. So, and this, by the way, is barrier synchronization. That's the, are you done, are you done, are you done, are you done? Also notice my code 503s are sitting there on an Xlog wait. And notice I have this thing running. XFS IO Livedemo is handling metadata. I want to come back to that in lecture. I got interrupts going on here. These things are always running, it looks like. I'm going to do an I, and I got rid of all the noise, so now I'm actually seeing my workload. And all these code 5s are sitting there sleeping on a wait. And then these code 2 MPs, some of them are running. I'm a little surprised. I thought I had threads on. There we are in threads on. And this is a case where doing it in batch with the -B, so that one of the problems on a large CPU system is you can't get 4096 lines on your screen to look at a system like this. Now you can consolidate by user and stuff like that, but it's kind of hard to work with 4096 threads that are running actively at the same time. Let me go back to here. So we were trying to find SDC. And I could have grepped for SDC as well. Here's SDC. So it's major minor number 832. And, I don't have, okay, one of the problems here is I don't have it by PM. The /dev/PM path is not visible here. Now this is LUN 12, but if I go into XVM, show-T-E on vol/*, these naming conventions are by dev PM. But then we have a number BDC0. Let's see if I can catch that. BDC0, where was, well, they're all coming out as SDC was a BE21, it looks like. Let's see if we can catch that here. BE21. So it looks like it is the third object within this stripe group. Also notice I have an external log, which is on D7C9, and D7C9 is SDE. Now I'm still a little surprised, right? Oh, this isn't sorting by failover path. And by the way, I've not configured failover on the system yet. So D7C9. D7C9 is also SDJ. I need to grab a piece of paper here. I'm going to grab a piece of paper and a pen and figure out this file system. So let's just look at it quickly here. LSCSI. So I have two root drives, SDK and SDL. With a DF, SDK is my root. And then I've got an SDL. And I don't see SDL mounted right now. I didn't do anything with it, Mike, because I was hoping you'd try the XVM lab on that one, but it's not mounted right now. And then I've got the same device. Notice they have the same LUN number here. So SDA and SDF are the same device. SDB and SDG, SDC and SDH, SDA, B, C, D, E, and I, and then what happened here? A, B, C, D, A, B, C, oh, I missed D. And then SDE is also SDJ. So I have 5 LUNs coming from that RAID device. Again, when you build the RAID LUNs, it asks you for a LUN number, and people will use a numbering scheme that tells, you know, they might go 10 through 14, and then they might jump to 20 to 30, but being able to use ranges of LUN numbers to sort out and make it easier to figure out which LUN is which. And we don't care about 31. Now, let me bring up VNC Viewer here. And with the reboot, Mike, it allowed me to come back in as display 0. And again, I do have a valid desktop with this connection. I don't know why we didn't have a desktop the other day. Again, maybe an out-of-memory event killed something.
Well, I came in on 1 this morning, and that had a valid desktop as well. So it was the 2, I think I used the 2 and a 3, which never had a valid desktop.
Yeah, and I'm not a VNC viewer expert either. Some of the other people and trainers use NX as well. Okay, so I've got 4 LUNs, but again, the reboot allowed the IS4000_bottom to actually be responsive now. This is where I hit the problem yesterday. Probably could have restarted the SMEE daemons and gotten it back, but I didn't think of that. And I had heard that there was a magma chassis alarm and stuff, so I wasn't thinking of restarting daemons. So I've clicked on this array. I'm just going to click on 1, and here I've got 3 drives, 3 drives, 3 drives, 3 drives, and then 1 drive. So I happen to have like 13, 3 times 4, 12, 13 drives that were in this cabinet or tray, and then there are 3 drives that are not there. Let me click on an individual drive. It tells me the volume group it's in, the location. I wanted properties too. Oops. So here I can see it's a 465 gig drive. They are SATA drives in this case, spinning at 7,200 RPM. Here's the product. That serial number can be looked up on the web or on the Seagate page. Now, if you notice, these are RAID 5. So here again, I named it Scratch 0. It's a RAID 5. And here we are, segment size, 128 KB. Make a note of these things. It's a 128 KB segment size. It's RAID 5 with 3 drives in it, which means it's going to be 2 times 128, which means it's a 256. Again, we have read cache enabled, write cache is enabled, and we're flushing data that is older than 10 seconds when we write to it. So this LUN is a 2+1 with a 128 KB. That means its strike width, or the optimal request size that we're going to try to match, is a 256 KB. Which was what? 262144, if I remember right, powers of 2. And I'm just looking at this one as well. And we can see the drives associated with it. This last one, then, is just a RAID 0. 1 drive. Any other questions right now? I was trying to find the actual LUN number for each of these things.
Oh.
The 10, 11, 12, 13, 14.
Gotta go to the map page, the house map.
Not sure why my this is behind. I'm not getting the oh, there it is, iconized. There we are. Thank you, Carlos. So here now I can see each of these and how they are mapped to what I'm seeing in LSCSI, the 10 through 14. You okay with this, Mike? Carlos has had some more background than me in this area. So I figured out each of those 4 LUNs and how they're built. By the way, while I'm here, one of the things that I have not done is also a PMG sys. And here I can now see things. These happen to be the virtual CPUs. That's one thing I don't like about this display. When you've got a hyperthread situation, there's no physical orientation to these displays. And I will do a PMG sys-V and direct it into, let's just call it PM scene. And now if I look at PM scene, I've got an ASCII file that is what generated this scene. And in a large CPU system, I can save all the overhead and continue to use this same thing. And I've gone into sites and actually modified them so that I can organize these between different CPU sets. Same thing with MPViz. So with MPViz, I can see what's going on here. And again, I see all these CPUs here with high system time. You do have the ability of let me click here, and rotating to look at it in a different way to get back behind things. And on your Floyds in the bin directory, I had built some of my own scenes for the USPS situation. Something like this one. Let's just see if it works. And here I'm just trying to look at this was for a much larger system, and these were organized in IRU capabilities and stuff like that. So here I'm able to look at system time on a node, I/O wait time on a node, memory free on a node. And I just built different types of scenes for a large system. Let me see if I can find the other one that I wanted, though. Let's try the MEM one. There's the one I was looking for. So again, I don't have a system this big right now, but this was tracking 2 racks. So I ordered the scene, so this would give me memory available, memory used on each particular node. I got node numbers here. This is an IRU here, this is an IRU here, the lower second rack IRU and the upper. And these were customized for that particular site. And then this would be like a node info type of command, but in a GUI. So if you look at these scripts, I basically took my scene, added this in front of it, and then customized the scene to be what I want. Let me back out of this now. I was on the desktop and thought I would point out those 2 things. This is a handy tool, particularly when you get into a super large, yellow, I can see some interrupt handler going on there. Okay, let me get out of there. So going back to here now, in ITSC XVM, there is a script here, XVM persistent name scan. And this is the one that's generating, and if you create your own custom script, you can change the naming convention within XVM. And they're basically like an LS-SCSI or something like that. So when I go into XVM, that is the script that is giving me this naming convention over here. And as of last November, we're using a dev PM type of thing. So looking at this now, I used a naming convention here that matched the Lund names that I did. So this was SDA and SDF, SDB and SDG, SDC and SDH, SDE and SDI, and then D and I, And then this one was the log, which is on SDE and SDJ, with 2 paths, failover paths going to them. And this is a stripe unit size of 512. So what's the file system characteristics here? It's going to be 4 times 512, that's in blocks, times 512 bytes to a block. So this is set up for a 1 megabyte request. So I had not matched to the RAID. What number would I need? And I don't know if you know Jeremy Higdon, but he's the one that strongly endorses matching the unit size to the stripe width of the RAID. So what number would I really want here?
What was the RAID?
The RAID was a 2+1 with a segment size of 128K. So I want this to match 256K, not 1 meg. So what number would I want?
No,
so
the 1 meg's the right stripe width, isn't it?
But we're trying to match the stripe width of the RAID, not the stripe width of the file system. So we're going to chunk it up, and this chunk should match what the LUN is configured for. So the LUN was 2 spindles plus a RAID times 128K, which is a 256, or actually 262.144. So we want this to match 262.114.
Right, down at the disk level. Yes, down at the bottom disk level.
62144.
28, because you've got 2 128K segments in each bit.
So at 262.114, well, something's going wrong here.
262.144.
144.
Yeah.
That's the size that the RAID is configured, the LUN is configured for a 256K byte to get broken up into 2 128K bytes. So we want to match 256K bytes. And if I divide by 512 bytes, because those were in blocks.
Well, each slice wants a 256K, doesn't it? Because there's 2 disks under each slice.
Yeah. So I am getting 512 here, so it is looking like I am matching. A 512 unit size is giving me a 256K byte chunk rather than a default of 64K byte chunk. So I don't know where my math went wrong before, but this is matching the stripe width of the LUN. And then the file system was 4 meg or 1 meg. So optimally, I'd like to do a 1 meg DMA request size that will get broken up into 4 256K byte request sizes by XVM, and then broken up into 2 128K byte request sizes by the RAID controller. Let's see.
And failover is not configured correctly, right?
Not yet, no. So I'm not putting the parity drives in here. So there's my 4 LUNs that are 2+1, and then I have a spare one here. So this one was SDA, SDF, and again, those things can change. This one is SDB, SDG, SDC, SDH. No, I'm sorry, my mistake. The LUN, both of these are SDA, SDF.
Exactly. 2 disks in each data.
What, 10? And then SDB, SDG, and I've only got 2 paths here, not 8, for example. And that one was 11. And then SDC. And to me, it's handy to have a spreadsheet so you don't have to go through this over and over, because top disk and star and stuff is going to show those names. And this was 12. And then I also had a 13 here. And then I also had a 14. SDD, SDI, which was 13. And then SDE, SDJ, and that one was 14. And again, each of these, the segment size that we're presenting to each of the drives was a 128 kbyte. So these 2 are meant for a 256 kbyte request size. Now here I am figuring out what request size a file system is optimal for, not figuring out what file system configuration would be optimal for a request. So I've already got a file system and I'm figuring out what it is considering friendly. And then these were put together as a stripe by XVM. So this 256K, that's times 2, because there's 2 data drives in there. We don't count the parity. So we want XVM stripe unit to match that. And then there's 4 of them. So if I do a 1 megabyte request, DMA from strace, that thing should be broken up into 4 256 kbyte stripe unit chunks. So we're looking at the fire bucket brigade, the IO chain here. And 256 would get presented to each of these, and then the RAID controller will segment them into 2 128 kbyte requests. And this last one here was the log, an external log. And the hard part is converting bytes, doing everything in powers of 2, converting bytes back to blocks and stuff like that. So a 1 megabyte request happened to be, what we have here, stripe unit was like 512 blocks. Okay, so that's like 256 blocks coming from the app that would get broken up into 4 512 kbyte blocks. So let me go back to my calculator, see if the numbers are still working. So 256 times 512 gives me a, oh, that's not quite right. What happened here?
512 times 512.
Thank you. Well, I was at a 256. What did I do wrong here?
Well, it's 512 blocks, so there's 512
Where did I get
blocks,
the 256 from?
512 bytes.
You're doing 256K there.
256 kbyte? I forget what I did. Lost track of myself, sorry.
So you done 512 basic blocks at 256K.
Yeah. So that was, let's go back then. So let's just multiply that times 2. I'm just getting the power of 2 correctly. So 262,114 kbytes times 4 stripe unit chunks gives me, oh, what did I do wrong again?
262,144.
oops. Four of them, and that gets me back to this 1 meg. Let's divide that by 512 to get back into blocks. So it's a 2048 block request that we want to see here. As long as you're understanding the arithmetic, even though I may be screwing up here. 1048. $576. Does this make sense? So I'm trying to going back to here, and I want to, I'm not going to get to it quite yet, but I figured out the file system design, basically, and then we'll get back to profiling it. Any questions right now? I think you were on top of it better than I was. Well, let's go back to what's going on the system. So I've just figured out the file system layout. Again, this did match what the LUN is configured for, which was a 2+1 with a 128 KB segment size. And then again, we have an external log. And if I cat my XFS tab, here is where I am specifying the log device when I mount it. We okay with all that? So I looked at CPU, I looked at memory real quickly, then I looked at disk, and I had to pull apart the file system to figure it out to continue with the disk. I'm going to bring up top disk now. And I now have mappings of the names for each LUN. So again, I am seeing STD busier than the others. Which is the fourth. And notice they're doing lots of little 4 KB average. Here's a 32 KB average, and these are just average numbers. I do have some reads, but in majority of the cases it is writes. And again, SDC, D, F, E, and J. I'm wondering about E. There's J. That's my journal. E and J. Notice that the log is acting different than the drive itself. C, D, F, G. And I got to warn you, we don't have failover configured, but we still have the path manager that is kind of doing a distribution to the closest affinity HBA, not necessarily a round robin order like you might have had before. Let me do something else here. IOStat-X 1-5. And again, the very first sample here, that was since boot. And I do have SDG showing me a whole bunch of requests that are being merged. A lot of writes. Again, my queue size, about 43 IOPS are queued up, but my service and wait times are okay. But my drive is kind of busy. So again, that would be a threshold trigger for me to say, okay, the drive's busy. Is it productive busy or is it non-productive busy? I'm seeing all this stuff. Now I want to do something else here. VI disk group. Oops, good enough. I'm going to say root is SDK and SCR is SDA, SDB, SDC, SDD. Let me just go SCR -HA, SDF, SDG, SDH, SDI. So that's the second path to it. And then I'm just going to do the log as SDE and SDJ. So I'm trying to group these drives together because it's too noisy. So now if I do an nmon-g on disk group,
Oh, you spelled it wrong.
I'm sorry?
Spelled disk group wrong. It's D-R-U-P-E. There you go. There you go.
Now I'm going to type in a G, and now I'm able to see my activity by grouping the disks together. So I can see that both paths to the RAID are being used. Block sizes are real small. I can see my log is separated out. We okay with this? Let me try a D. And here on D now, see the thing I don't like is I've got the same device twice. But here now I can see my high water marks, but the trouble is with a large disk farm, you can't see everything. And I wish I could filter this out, which is why I was using the -G. And let me go back to my desktop here. Oops, I should have kept that up. DKViz. And again, I would, on the system, save the ASCII output so I don't have to generate the ASCII file. And again, this is not organized very well. This is just alphabetical with a certain depth. In the old days, it would actually be physically located so you could tell what HBA something was on. So I could go in and change the scene for my site and make the scene physically oriented. Also, I am clipping here. These whites say it clipped. So I adjusted the scale. Wrong direction. There we are. And again, if these drives go busy, even that one clipped. SDG, SDF. If you look up in the box up here, you'll be able to tell what drive that's coming from. SDC, SDD, SDF. So I can actually see it being spread. These are the HBA, first port on the HBA. This is the second port. I'm even still clipping here. Okay, so I see these. We went through CPU, we went through memory, and I spent a little bit more time on disk right now, which is where we are with I/O. And I've now mapped those devices back to the file system. I know that this is all /scratch across two different ports. And where was my PMG sys? You can see it going on here as well. But there's no it's not easy to physically figure out what those things are, which is why I was using nmon to give me a better idea of what these drives are, to organize the data into something that's more meaningful. Okay, so I/O top. So we have disk activity going, and I see an XFS buff D, which is for XFS, writing to XVM0, and I still have to figure out what XVM0 is. And I see all these code 503s. Numbers look pretty good here. None of them are in terabytes or petabytes or anything like that. And again, this data is coming out of proc PID, the I/O file. Okay, so I see all those code 503s. Let's do an fuser-uvm on /scr, because we know that's the file system that was busy from the SAR report, or top disk. Had some sort of NFS stale area there, but now I can see all these code 5s here running. Let's see how many we have running. Over 1,000 of them. I go back here with my top, there's my load level. And if you look at them, a lot of them are in a sleep situation, and this is a metadata wait. And there's the daemon that's handling that metadata. AIL stands for Action Item List. I was expecting to see the log a little bit hotter here as well. And by the way, there are things we can do about that, increasing the size of our log buffers and stuff. Okay, so now let's do an S-trace on one of those things. Let's just pick one, 50248. One of the things you can do, maybe I'll do it this way, PS tree-P, let's see if we can grep for code 5, find the parent. I can't see the parent there. I don't want the grep. Ouch, I got all those code 2MP statics too. There we are, code 503, the parent is 12275. So now if I do an S-trace, -F to follow the children, -O to save the output, -P, and then I'm putting in the parent PID, 12275. And unfortunately, S-trace writes to standard error, so you can't really page it or grep it easily. That's why I'm just dumping it into a file, particularly when I got this many children's. And again, attaching to S-trace is going to throttle back these applications. Let's take a look more on file. Oops, what happened? The F should have followed the children, and it doesn't look like it did. 12275. We do get the parent, and we're seeing the way to the parent, but we're not seeing all the children from it. I would have expected that to actually follow everything. I think maybe I needed to catch it when it actually started, not after. The forks have already occurred, so I'm not able to actually catch them. So let me just try a 12301. Again, these are just in a wait state. If I start the S-trace before the forks, then it would have seen the forks and followed the children. But in this case, I can't see them all. So let's try a 123. I'm just picking one randomly. And I want to break out and put in a couple of T's. So now I can see that application is doing makeDirs. This is the name of the directory it's creating. Here's the return status, successful. Remember the other day they were not. And then this is the elapsed time or wall clock time that that system call took, not the system time. Let's do a watch df-I, since I'm seeing metadata everywhere. And I can see that the Scratch file system has a lot of metadata activity going on to it. So we've traced the I/O back from a device being busy, figured out the file system layout, used fuser and I/O top to identify what was doing I/O there, and then we're able to actually look with S-trace at that particular process to figure out the nature of the I/O that it's doing. Any questions right now? So there is a stat file here for XFS. PCP can get to this data. If you do a PM info -T, let's grep for XFS. And then you can see all the statistics that are available out of PCP. I'm going to get into this in the next module. But here in particular are my directory information. Now I have my own script that's going to visualize this data now. Let me Q. You have to hit a Q to quit. If I break out of it, it will continue running. Let me drop my fonts down. so I don't get a line wrap. I'm still ugly here. Let's see. There we go. That looks pretty good now. So this is characterizing my XFS as one total for all XFS file systems. You can't split it out on a per file system basis. And again, I can plot this data. It's kind of interesting to me. So here's the action item list statistics that we were seeing from the daemon going. Here's my directory lookup, directory creates. I'm not doing any LSs or get directory entries. I'm not removing any directories right now. Not a whole lot of data. There's no allocations going on. There's no deallocations going on. Log activity. In particular, by the way, no IC logs. There we are, no IC logs. That's what that XFS log wait is. We're waiting for a buffer in memory. The buffers in memory for the log are highly contended for. Now remember, extended 3, extended 4 could use all of memory for the logs, and that was buffmem. But XFS has a fixed size for these buffers, so we've got a lot of contention going on there. If this was a normal bread and butter workload, I'd want to reduce those no IC logs. And here's the amount of log activity. So I definitely have a hot log. Everything, all of those are dealing with the log activity itself. And I can see a lot of metadata activity, but no real data activity. Not a whole lot of inode activity either. Okay, everything is directory intensive for this situation right now. Down here we also have vnode activity. So again, since I don't have inodes, I'm not seeing any vnode activity. And then here's my page cache, my buffer cache. And of interest to me, here we're trying to get buffers. A bunch of them were locked, and a bunch of them were busy and locked. So there's contention on the page cache as well. I'm going to come back to these later. Some of these I don't care about. These are more for internals people. B-tree lookups, block mapping, more B-tree lookups. B-tree is a search algorithm through the file system. We'll talk about a B-tree. I kind of like to compare a B-tree to like a roundabout in England. Before you hit the roundabout, you got a sign to say which spoke to take to get somewhere. A B-tree basically is a sign at the fork of the road at each directory fork to figure out what's the best way to go to reduce my searching. So I do see metadata intensive activity here. I'm going to quit and get out of there. I quit wrong, so I got to kill the thing. Let me just log out and log back in. Let me put myself into the global again. Okay, so where we were, we just now characterized the I/O that's going onto that file system, and it was lots of little I/Os, all metadata and make drs. And XFS statistics confirm that. Now moving on though in my analysis, I just want to do a cat on /proc/meminfo and look at more detail here. So most of my memory is free, a little bit of buffers, 128 mega cache, not bad. There's my swap cached. Most of my data is active, and most of it is process space that's active. But that's less than a gig, and very little file system. By the way, I want to check something here with PCP. There's the system time we're seeing, a little bit of swap. There's my memory again. And when we look at it, The slab now is at 40 gig. Little surprised about that. And most of it is reclaimable, but there is 7 gig that is not reclaimable. No dirty, that's insignificant. No write back, we'll get back to that in buffer cache. Anon pages, some shemem or map, very little shemem though. Let me do it ls-l and /dev/shemem. This is for audio actually, and nothing important there. IPCS-AM, nothing unattached. So shemem is not an issue right now. The one I need though is ninfo. Oops. Again, this is a modified node info where I've added shemem into the display. And here again, this is what we were talking about, Mike. Here's the free, so I've still got 600 meg free on node 0. And most of that memory is consumed by the slab. Okay? Let's do a slab top -S space C. And this again correlates. Now the other day it was an extended 3 that I bombed it with. Now I'm bombing it with XFS. And ironically, I am seeing a lot of inodes in here versus directory entries, but we were seeing a lot of make ders, and the XFS, was showing, XFS stats was showing metadata on directories more than on files. But we have a lot of inodes, 30 gig it looks like are inodes in there. What's my top doing? So there's my journaling activity. And we could even see the IO characteristics were different to that. Oh, let me bring up top again. The RAID device had different IO, or the log device had different IO characteristics. But here's that XFS log weight because of the no IC logs that we saw. If you do a man, and I disagree with this, man on mount, let's go to /log buff. That should do it. In XFS, we can specify how many log buffers we want, but the default is the maximum. We can only go from 2 to 8. I wish that I could go larger than 8 buffers. That would reduce the no IC log storm that I've got going on right now. And also then the size of these in-memory buffers. So again, this is what was different. Extended 3 had no limit to these. XFS does. And that makes extended 3.4 a little bit better in a metadata intensive situation like this because it's not going to hit a memory pressure. And even though I've gotten the log off of the production data disks, I still have contention for the log itself in memory itself. And we have a 4 KB block size by default. I'm just looking here. So I'm a version 2 log, I believe. Oh, the default for any recent kernel is 32K. So I've got 8 32K buffers for my journaling activity to buffer it in memory before I flush it to disk. And basically the recent kernels have upped it to the max that you can go. So there's no tuning opportunity left anymore. Let's do a cat on /proc/mounts. And where was that file system right here? By the way, I do see stripe unit and stripe width. Let me do an XFS_info. Do it as a -R, I believe. Oops, I guess I don't have to. So here were the makeFS characteristics. And the log is external. It is a version 2. My data file system has 32 allocation groups across 4, so that's 8 allocation groups per LUN. And then here's my number again. My stripe width and or stripe unit and stripe width. So what is that in bytes? 64 times what?
40.
On 4K, the file system block size.
This is a misuse of the word block. They're talking about file system allocation sizes. And there we are. There's my stripe width that we computed before. Now, these two numbers, by the way, are only used by applications that ask for it. RPM-QA, let's rep for XFS. Let me go into YAST. I'm going to need to take a break here soon. XFS. There's what I need. I may as well load XFS dump too. But here's the one that we needed for the XFS CTL stuff. So those numbers that are in the super block are a way for an application to ask the file system, what do you consider well-formed friendly I/O? Not all applications do that. So this XFS CTL, in particular, DIO info, returning the direct I/O characteristics. Let's see, since we no longer have buffer cache in the middle, so the data buffer has to be sectorized by the programmer and has to be on block size multiples. So this will actually return you things of your memory alignment requirements, the I/O request size, and multiple of that size to be sectorized already. If I am not sectorized properly, the read or write will fail. So XFS CTL has a whole bunch of things, but that DIO info is what's going to get this back. This is where DIO info gets itself. Then the application can set itself to be a 256 or 1 megabyte request size. Any questions right now? So we're seeing with strace, make-ders. Let's go back to my slide here. So in this area, we're seeing nothing but make-ders at the system call level. We see that it's XFS, and we are seeing inodes and directories and journaling and slab activity. And again, I did not do, there's a *V that would show me the number of inodes and directories that are in the slab. And the slab is not handled by dirty ratio or dirty background ratio, but a sync would flush the slab. Now let me come back to those later. We figured out the topology of the RAIDs and the topology of XVM. Let me go into here, do something. XVM, show-H, or I'm sorry, help-H on show. Oops. Let's just try help show. Help-V, is it? That was -H. Show-H. Oh, come on. I haven't done this for a while, I guess. There we are. Show-V for verbose on the help. So I can show-stack. And here are the statistics that getting out, but again, these aren't, I don't really care about that. I can get that out of PCP and stuff like that. But for the stripe volume, the scratch thing, Here's all my reads and writes, so I can see I'm reading more than writing actually, even though I'm seeing a lot of make-ders. But blocks written, these are number of IOPS. So I'm seeing lots of little reads, but I'm seeing a few large writes because of the blocks written. And none of them are coming out stripe aligned. Most of them are coming out aligned, but smaller than stripe width. So most of them are coming out smaller than 512K. And a majority of them are coming out unaligned. Do you remember the threshold at which we switch from unaligned to aligned? What file size do we switch to alignment? 512K. So if my files are smaller than 512K, they're not going to be aligned. But I guess I am seeing alignment here and here. Now, I do need to also do this. Let me get out of here. I'm going to go into /sys/block. And notice I have an XVM0 and an XVM1.
Can't see the desktop here.
Oh, I'm sorry. Jump in. I wonder how long I was there.
Not long.
So I had gone into a XVM, did a show stat to look at all the statistics, and in particular what I was looking at was this particular group. And these are basically meaningless nowadays, but everything is coming in. So here I was saying I got whatever, 389 million reads, 158 million writes. But if you divide by requests into blocks read, it's basically lots of little reads, but it does look like it's large writes. And I got to warn you, this includes the journal. This is all objects within the file system. I can't separate the journal out. So what I wanted to do then was to go look at the blocking layer here. I'm going to go into sysblock, and there's an XVM in there. And sometimes you got to be careful because you got to map major minor numbers. XVM may have major minor numbers and things like var log messages. And in there then I've got vol info. So I'm going to do a grep of null. Oh, why didn't I get a 1? So XVM0 is my data subvolume for Scratch. But why didn't I see one for the log? Oh, there's a XVM1-1 in there now. I don't remember that before. Was that an L? That's an L. I don't remember that before. Let me just get rid of this. Now I can see 0 is a data, 1 is a log. So let me go into the data one, cd to xvm-0. I'm going to go into Q. I'm going to cat max sector k bytes. Oops. And 256 k byte is what the XVM is going to do. So it can get blocked before I get to the device driver itself. Let's cat HW, and I can go up to a 4 megabyte request size. That's the maximum. And by the way, while I'm here, ITSI dev-attr, dev-attr.conf. So these were an IS type of device. Let's see, we got SGIs, anything that is an IS type of device. Note we have changed the scheduler to a no-op here. Turned off the scheduler. Also, I'm up here, let's see, this is an IS, so my max sector k byte should have been 2048. But again, this does not support XVM yet. My root disks are at 1 megabyte. Maxtor drives, 256 kbyte. Okay. So I can't change XVM here. Let me go into Q here. Let's cat max underscore sector kbytes, and there we are at 2048, and that's what we had up here. That 2048 got set by a rule that is this dev-attr rules. But again, that does not support an XVM. I wonder what this is going to do. Oh, that's not what I wanted. udev. Let's see, it was 48. So I think all this is just naming convention. Nothing in there that's going to support XVM being configured by the dev-attr that I'm seeing. I want to take a break here real quick. Give me a few minutes. Let's cat nr. That's still at 128. Let's cat the read ahead. 512. Again, it's twice the stripe unit. Stripe unit was 256. So it's twice that. And I don't think I care about anything else here. Let's finish this analysis here. SAR 1-5. Remember, I still had system time in here. So I'm going to try a perf top to look at that system time. Remember, early in the week, the system time was from the failure of the makers. I do see some system time in here for mem copy, some zone allocation, but most of it seems to be this raw spin lock. Here's my log activity. Mem copy still. Updating the load level. 5% of my system time is just updating the load level average. By the way, I want to check something here. Going back to PCP, I am getting occasional slab scans. So here you are, Mike. We're talking about trims, and the trim of the slab we saw was slow last week. And look at how big the slab is and the impact when we're doing 50,000 scans on the slab. And for page faults, I am getting some page faults here and some page freeze. Let me get rid of those. Really can't, everything else is still buried in noise. And I do have some swap in and swap outs going on. And look at what the Numalink traffic is doing, and if I could correlate that to the disk activity and the writes that are going on. Again, I still have a large slab. How is, let me do a top sys. So this is showing me my system time is primarily, again, metadata activity. This is basically an interrupt handler. It used to be called event-D. But code 5s, and again, everything I see here is metadata intensive. The code 2 MPs have finished, by the way. Okay, why don't we take a break here? I got 25 after the hour. So I was kind of spending time in this area. I want to come back from break and do direct I/O. I kind of did a quick analysis. We looked at strace, we looked at XFS stats, we were briefly looking at SAR-B, SAR-R, we looked at XVM statistics, top disk. We have not done block trace yet. Let me save that for direct I/O. So let's come back in 15 minutes at 20 to the hour. Is that okay with everyone?
Yeah.
So reflection after break, are there any questions right now? Now during break, again, I'm going to wrap up with this. I want to finish the analysis and then do the direct I/O demo. And then we need to jump to XFS, take another break, and then talk buffer cache. So I may assign you the time. If you look at you should see on the screen that I/O stages, where I'm trying to write down the information about each of the steps or stages in the I/O path to figure out what the attributes are, and I want to get back to this with direct I/O. We were doing it with metadata I/O previously. So let me go back to my demo. And I did do something differently during break. So I've got top running here. Let me get rid of this stuff. So if I go here, look at what's happening with the system now. What are you seeing? What's the behavior? The CPUs, we got what? Lots of system time. Swap looks okay. By the way, let me do this. That trickle swap, I'm going to do a swap off -A. I would not normally do it on a heavily loaded system. We're waiting for the swap off to finish. And maybe I don't. I'm probably not going to be able to break out of that either. Yeah, I did break out of it. It never finished it. I'm not sure I want to continue with that right now with the load on the system. Again, memory, I'm in a CPU set situation. Now, one of the things I should tell you about, I have my own little script to give me information on a per CPU set basis. So I've got a root CPU set that's everything, 8 nodes, 64 CPUs. We'll come back to the exclusives say nobody can come into mine. This is broken. This actually is behaving like a 1, not a 0. And this is what I was talking about later. This is what's going to do an interleave on my page cache, which might be bad on a 256 node machine spreading everything across the entire system. But if I'm in a CPU set, it only spreads across the CPU set. So, for example, USPS is not using CPU sets. It's an Oracle situation, and they've turned these off so that they have latency, which is good, unless they start busting the node and have problems with the slab getting too big, which they were, and also SHMEM type of stuff filling up a node. That would create a problem. These are all the threads. I don't care about those right now. And then I've got these things too. And then I've got my next CPU set, which is the login CPU set. Looks like everything is 0 here. That surprises me, huh? Normally the child is inheriting the parent. I'm going to have to look at that. That does not look right. So within the login CPU set, I've got all these code 5s running. bunch of Java. I don't have PBS running, so there's nothing in there. Now PBS will set its own flags. So all that is probably from PBS doing it. Some sites will have a set UID program that can toggle these things. And again, hardwall isn't working. And then my boot CPU set. And again, that's going to spread just within the boot CPU set, keeping it all on node 0. I also have a -V capability. The script can actually do it by job ID as well. So what I was trying to do was be able to get a report on all the PIDs in a PBS job ID in a particular CPU set that I could name the CPU set. But let me just do a more here. And I do have a problem. PS-P will work on a process ID, but not a thread ID. I wonder if I should, let me echo $$ into /dev CPU set /tasks. Okay. This is running rather slow for me. A lot of this is running PS, and we're doing on all the kernel threads as well, and grepping a PS output. There is, with Slurm, a cache feature for PS data, so we don't have to keep pounding on the proc PS or /proc PID for all the kernel threads. That ain't happening. I'm not sure I want to continue with that. Let's see what we got going here. Let's see if we can catch it here. Again, top is having trouble coming up as well. There, we started getting some top stuff. Oh, I got a bug or something in there. I think I'll just ignore that right now. Here's my top. My CPU set is actually running. The program is either running, runnable, or sleeping, and I'm seeing nothing but running here. There we've got a pipe wait going on. By the way, again, I have 88% system time now, and I've got that program code 2MP running. Notice %CPU is greater than 100. And for both of you, the latest top, older tops would truncate at 999, and 999 means that you have reached the maximum number of characters the top would print. But that has been fixed in the latest top command. And that simply means we're multi-threaded. Let me do a capital H. By the way, that's a 7-second program normally, code 2. And look at how much CPU time is consumed already. So when you see %CPU greater than 100, look for threading. And now I can see the threading. This is my barrier synchronization. I have a barrier synchronization problem here. So few text wait is the phone call saying, are you done? And again, there are two types of synchronizations, a spin, and I just sit there, are you done, are you done, are you done, are you done, and that shows up as user time. But there's also a, are you done, are you done, are you done, yield the CPU with a sched yield. And SGI's MPT is a spin barrier, but Intel are yield barriers. So looking at that system time, I'm just going to do a top sys first. And there we are. All that system time is due to these code 2 MPs. Now I'm going to do a perf top. By the way, go ahead and try your own perf top. I'd like to see 3 perf tops running right now. I'm going to fire up another perf top myself. Again, when you are in a tight situation, I would not do anything serious on the serial console. A sync command or other commands could hang, and then you don't have a usable serial console. You can't always break out of everything. You cannot break out of a middle of an I.O. The D state, non-interruptible. You see what I got going on back here. High system time. We already know we're in a memory pressure from the slab. Mostly writes, which appeared to be the make ders. And here now I have my system time. And this system time is a barrier synchronization problem. This is the the Intel libraries, the _KMP, Cook Associates. And here's where the Intel library is doing a sched yield. Sched yield results in the CPU scheduler waking up. So here I have the CPU scheduler showing up, and in particular, thread return is my context switching. There should be something like a put previous task on the queue, switch to, finish task switch. Here's the sched yields. So I am thrashing right now on sched yields and driving. All that system time is due to the CPU scheduler going crazy from sched yields. Let me do a ps-e mt. Let's grep for code 2 MP. Now, system time is creating contention right now. Oh, what happened here? I want a better PID. Here's that perf top again. Okay, there's a code 2MP static. Let me do a perf record -P. I'll just pick 59737. I'm just randomly picking one. And again, this is a case where I'm just going to wait a little bit and then break out. By the way, perf will not know if the process goes away. It will continue running. I have a bug on that. Okay, so I've just picked one. I might have done it by a top sys as well. Taking a while to break out. Don't worry about this because I am driving the system crazy. They're going to lose. It can't keep up with all the events that I'm causing here. What do we have here? Oh, darn it. I was afraid of this. Oh no. I missed part of it. I was looking for the dazed and confused message, but instead I got a panic. So I've got to deal with this right now. We'll go to lecture here, but I basically lost my system trying to look at barrier synchronization and using perf tops and stuff. And this is exactly why I'm trying to run this stuff in a class like this, because I'm really using it and deliberately trying to trip over problems. So pipe TEE, I'm just going to call this second panic. Those that know Hetty, he's going to say, not again. Okay, UVCon steel P3, arch KDB. This was tight VNC. Let me just get rid of that. Lost my desktop. So I was trying to create a job mix with both metadata, and one of the things I was trying to get to there was sched yield was causing context switching. A SAR-W would have showed context switching, which is why perf top was losing events and stuff like that. Okay, so now we're into the D message. VT. So it made a sched yield system call, took a non-maskable interrupt while it was in the scheduler, and panicked. BTA. So I'm going to have to open up another PV on this one. But that's why I was on the console, because I knew when I had large clone, high thread count, and start using perf, though I don't know if this was a perf one, that will trip some of these NMI problems. All the NMI code was rewritten with the 3.0 code, so that's why I'm spending a lot of time in that particular area trying to stress it, and I am deliberately trying to panic it, I admit that. Better now than when it's out in production. So anyways, let me get this thing rebooted, but then I'm going to go to lecture. That's 3 panics this week. By the way, for both of you, the panic I did in XVM last night, XVM has some in /sbin, some PM underscore scripts. They're not meant to be run by administrators, but I saw a PM underscore show, figured I'd run it, and it panicked the system, and there is a PV on that. But I have to discourage anybody, you know, as an administrator, you see new commands and you want to find out what they're about. And they had a usage, there's no man page, but then when I actually fired it up, it panicked last night. And this event with the barrier synchronization problem was meant to be a preparation for tomorrow when we get into this more. Log activity. I had so much running. Not as bad as that million process storm we had the other day. See if we can catch one of these tracebacks here. So here's an example, one of the code 5s. Starting off with the system call, it does a make dir, a make node, a create. But then notice it does a transaction reserve. So every time we make metadata changes, we coalesce them into a transaction. And then we're going into this xlog grant log space. But because the logs are so contended for, we go into an xlog wait. An xlog wait is what we were seeing in the top wchan field. I was hoping I'd just get a dazed and confused, not an actual panic. Oh, how much longer do I want to wait? So this one is a dead window now. The last snapshot I got from perf top, this was all context switching, returning back to the prior scheduler. This has been a hot subject. There are possibly problems in this area still, but it's taking a lot of time, consuming too much time. And there's still a PV open on that one. Here's the CPU scheduler waking up. Here's a spin lock of some sort that it was using. Here's the CPU scheduler wake up. What happened here? Okay, K-dump. And then here, notice it says over here what's the kernel or the program. Underscore KMP is the Intel Cook Associates OpenMP libraries. And this is the barrier stuff. So it does a yield and a pause. So we say, are you done, are you done, are you done? And then we make the yield. And here's the actual sched yield occurring. Here's the CPU scheduler again. Here's the sched yield itself. Here's the CPU scheduler clock going off. Here's the CPU scheduler again, the sched yield coming from the application. And here's a context switch as well. So all that system time is primarily sched yield causing context switching and the scheduler to go nuts. Okay, let me go to lecture here. Let that thing reboot. So I want to go to XFS. I'm going to stop the recorder.